Hi.今天学员出动了，基本上。Did you register? I still have not registered. Most likely I will.
What did I say?
I did not reply.
Did not reply?
I did not reply. I think I'll go for it.
You did not sleep well.
Me?
Yeah, I can tell. Your eye.
Yes, I stayed late yesterday.
Okay. So what we're going to do to cover today is the basics of least squares solution to overdetermined ill-posed and inconsistent systems of equations. We'll do the formal least squares solution of one of these systems. We'll then show you the iterative steepest descent approximation to that. In the machine learning literature, they'll call that a gradient descent. And there's more than one type of gradient descent type solution. This is the most primitive one, and it always surprises me that they can get away with that. If you work in something like geophysics and seismic conversion, you never use just a steepest descent. You always use some tricks to it, like quasi-Newton and preconditions, but we're not going to get into that. We'll look at some properties of these systems of equations and their solutions. One is regularization. The other is, we'll look at overfitting, something that Shu Yu talked about. Look at scaling. And then we'll end up with the summary. All will be done in the next hour, and if nobody comes in the next hour, maybe a little bit more. So let's start off with least squares solutions and define these types of equations. So let's define an equation, a set of equations. M1 is equal to 1, M2 is equal to 2. Oops. And another equation, which is M2 is equal to M2 is equal to let's try 1. Okay. So this is a system of equations where the unknowns are M1, M2. And in my notes here, I'm not going to take the time to go vector over that, but usually I indicate vectors with strong, a bold-faced version of M. So let's first ask this question: what's the solution to this set of equations, Abdullah? 1-1. So there's a solution. So Abdullah claims the solution to this system of equations is 1-1. And how did you come up with that idea?
M1 equal to 1, M2 equal to 1.
What?
So obvious from M1 is equal to 1.
Okay, M1 is equal to 1,
One,
M1.
The second equation gave the same solution.
Okay, so that's a solution to that.
Over
And,
determined system.
okay, so there is a solution, and we call that a consistent set of equations. On the other hand, if we had a set of equations that was given by that, what's the solution to that set of equations?
It's inconsistent.
No, I'm not asking for a fancy word. Either yes, is there a solution to that set of equations? No. Okay, so there is no solution. So are we stuck with that? Well, let's plot this up in a space of possible solutions. Space of possible solutions is any values of M1 along the real line and M2 along the real line, or orthogonal axis here. And so this guy, the solutions to this guy plots out as a line. Okay? So in this case, M2 could take on many different values, and yet it's still the solution to the first equation. And the possible solutions to this equation is M1 is equal to 2. Now, if these guys intersected, then you would have a common solution to this, here we don't. And then we plot out this guy, and say that's 1, that's 2. And any point along this line is a solution to the second equation. Okay? And obviously, you don't have a common intersection point of all three lines. And that means it's an inconsistent set of equations. So no solution exists. So do we give up? It turns out this is the case with all of geophysics, real world geophysics, that deal with real data. We typically have overdetermined, and we have overdetermined because let's create the matrix vector multiplication associated with this guy. And so the first one would be 1, 0, 0, 1. And on the right hand side, look man,
1, 2, 1.
1, 2, 1. Okay. So we can call this guy L, matrix, this guy the M, vector, and this guy the D. Okay. So when you have an overdetermined system of equations, and we consider this to be a M by N matrix, and this to be a N by 1 vector, and this to be a, what's the, let's call it D. Let's call it an M by 1 vector. When this guy is taller than it is fatter, it's an overdetermined system of equations. There's more equations than lines. And that's typically the case we deal with in geophysics, or probably any kind of field where you take measurements in the real world and there's errors. And such errors lead to inconsistent sets of equations. Even if we don't have errors, we might not have the right physics. And so the L matrix doesn't really explain the data like it should, because we left off some physics. That could also lead to inconsistent sets of equations. So what would be your next best thing, since you're a real world scientist, look man, what's the best guess solution you might consider that you'd go with? That might satisfy sort of means approximately all three equations in some sense. Tell me where to stop my finger.
So somewhere here.
Huh? Here?
Yes.
Okay, or maybe here, depending on what the right-hand side is, okay? So your intuition was sort of, well, it's close enough to all three lines, and anything close enough to all three lines, even though it might not even be on one of the lines or two of the lines, exactly. And what he did was to create a penalty function in his mind that penalized solutions way out here, very far away from the intersection, a common intersection point, or sort of common intersection point, and rewarded anything that's close to this. And one such penalty function is a sum of the squared residuals. And this guy is called the residual vector, and it's a difference between the predicted outcome and the actual outcome, or the predicted output and the actual or observed output. Why do we call this a prediction? Look, Matt. Why do we call this the observed?
Because we already know the solution.
Yeah, we're done with that.
Yes.
We went out in the field, we collected, so we can call this D. I think, do you know if this is D just for out of randomness? Consider this the D that's fixed, that's what you measure in all its glory, all the errors you have in it. Whereas this guy is a prediction trying to match some kind of model, the M's, that will try to match the predicted data with the observed data. Okay. So one thing that Lookman could have done was just try different models and then look at the error values here. And he wants really, what's your desired errors here you want, in theory?
Minimum.
0.
Yeah.
Okay. So you can try that, and that you can do a lot of trial and error estimations. And this is a very long vector. He's going to lose his eyesight looking for the zeros and the things that are close to 0. So a better way to do that was to look for a penalty term that could summarize the errors in one scalar value, and that's what this is. And what this is the length of the residual vector squared. Here's the residual vector. You take the transpose and the dot product of it with the residual vector. Okay, so visually, what he did was to take this plot and flip it 90 degrees and plot out his data penalty term, or sometimes we call it the data misfit. This is a data misfit because if this is non-zero, that means it indicates that your predicted data is misfitting the observed data. So how could you create this epsilon here? What he does, he has a table, and he has different models, and he has different predicted data. And from the predicted data, he can get a residual, and then find the squared length of that residual. So what's your first guess as a predicted model? How about 0, 0? He has a 0, 0 vector. He plugs it into this equation up here. He gets a residual that's non-zero, and then he takes the length of that guy, and he has a computation. So that prediction is going to be 0, 0, 0. And the length of that guy, what's the length of that guy, Luckman?
6.
What's 0 minus that? What's the length of that residual vector?
2.
Okay. And he got 2 because he took 4, squared this, got 4, added to the 4, 1, another 1, and he got 2.
No.
He got a 6.
6, yes.
Oh, he got an 8?
6.
See, I think he's real nervous. Okay, so he plots up an 6 up here. And then we go through different trials. And as we try this one, and he gets something like that. tries this as a guess solution. And he does a Monte Carlo search for different solutions. And pretty soon what he gets is this cloud of points that define the surface, an air surface. And if I were to fill in all the points here, get rid of some of the distracting, if I were to connect all the points with lines, you get this air surface. Which indicates how badly you did when you used the model over here compared to the model over there. And what he did was to find the best model was look at the very bottom of this air bowl, this air surface. He went ahead and contoured up the elevation, the height of this air surface along the M1, M2 axis. And that bottom of the air bowl would be the best solution. In fact, the best solution is probably going to be around here. Okay, so if I were to rotate this around, that surface would be like that, and the M1 would be, let me draw in the M1 line